Good evening, everybody. My name is Dr. Chris Murphy. You may know me as the admissions tutor for physics and for engineering here at the University of York. I'm also a laser plasma physicist, but tonight I am acting as chair for one of our webinar series. So the webinar series, a few technical notes before we get started. Before I introduce the speaker, if you're watching live, you can ask questions at any time during the seminar by clicking on the Q&A button at the bottom of your screen. That'll be available throughout the event. So just ask questions at any time. I'll put those questions to our speaker at the end. Should you have any technical issues, such as loss of Wi-Fi or any other problems like that, you can rejoin the event using the original link that you had in the email. Please remember that today's event is being recorded, so if you miss anything, or if you'd like to repeat it or show it to some friends, you can always do that, and you'll get a link to that at a later time. There are also subtitles available. If you want to switch them on or off, you can use the CC Show Captions button at the bottom of the screen as well. So in this webinar series, we'll be bringing you cutting-edge research from the School of Physics, Engineering and Technology at the University of York to give you a glimpse of some of the range of exciting areas that our physicists and engineers are currently working on. You can keep up to date with upcoming lectures on the webpage, and you can watch previous webinars on our YouTube channel. You'll find the links in the resources tab at the screen as well, so you can have a look at that at some point. So now on to tonight's event. It's my pleasure to introduce Dr. Manish Chauhan. After doing his PhD in Italy, Manish worked as a Marie Curie Fellow at the Storm Lab at the University of Leeds. He then moved to join us here at the School of Physics, Engineering and Technology in York as a lecturer in medical engineering, where his robotics engineering is applied to everything from molecular biology to quantum physics and everything in between, pretty much. Manish is going to talk to us tonight about the use of robotics for medical applications. He'll talk about how robotics are being used for cancer diagnosis and rehabilitation of patients with a range of conditions. So I'm going to stop talking now and hand over to Manish and welcome him to our seminar series. And if you can share your screen, and hopefully we will be good to go there. And at the end, I will see you again for the Q&A and to round up at the end. Thanks,
Many,
Manish.
many thanks for the introduction. Uh, Good evening, everyone. Um, as you all know, my name is Manish Chauhan. I'm a lecturer in medical engineering at the University of York in the School of Physics, Engineering and Technology. Today, I'm going to talk about some of the exciting areas in medical robotics, which have potential to shape up the future of healthcare. Uh, I name my topic as robotics engineering in associative medical applications because robotics in itself as corely cannot solve all the problems in medical domain. It can be worked, it can work as a team player with other methods of diagnosis, which which are available from other research community members who are doing wonderful work. So most of my work, which you will see today, is more about an integrative approach where we are working with different people in different domains, and we are presenting some solutions for some most challenging medical problems. So I'll tell you more about what I'm going to speak, but my topic today will be divided into uh, three main areas. One is soft robots as an importance. Why is it so important? And then some of the applications of soft robots for diagnostics and rehabilitation. So uh, I'll begin with it by saying that what do soft robots literally mean? Uh, like you what Generally what happens is when we talk about robots, the first thing which comes to our mind is something like a very rigid robot which has a very big base, and it has some links which are connected with some big motors, and it has a big end which can move, and it can hold some object like pinch it, pierce it, or even hold and rotate it. Such big machines are used in assembly lines in automotive industry or even in food packaging industry, where they use big conveyor belts and automatically distribute different kind of um, packaging material or food items into separate packets. When it comes to automotive industry, such big robots can be used for welding of specific areas on the car chassis, which is very difficult to access with humans. Then there are robots like these, something like a KUKA robot, which you see on the orange and grayish on the left of my screen, second left image. Such a robot is used for medical applications. We have in our department a medical grade KUKA arm, which can be used for even uh, robotic operations or surgery on patients. And why this? Because such big robots on the left with the black colored image, which you see, they are very rigid, they are very heavy. If there are incidences where people are trying to work along with a robot and the robot goes out of control, and it may cause an unfortunate accident for the person who is working with it. So it is very important that a robot has to be compliant in working along with a human in a real world environment. And such cases or such um, applications are promoted by such new robots, which like a KUKA robot is shown on my screen, that can work along with patients or doctors. And even if it goes out of control, the human has a control over it, and it can pull it back, or it can even push it back. It won't have enough force to kill a person, or it doesn't have enough force to harm or injure or inherently cause any injury to the patient or the doctor. Now the things have gone further advanced, and now people are developing into some soft material robots, which can basically bend or flex like a human muscle. And that's where the robots are most useful, because they can be compliant with a human being. Suppose you are creating a robot which can basically touch your skin, your hand, and at the moment you try to bend it or push it, it just bends along with it. They are not designed to basically go against the force of a human, but they are designed to go compliant with the human interaction. So if I do a comparison between a rigid robot and a soft robot, a rigid robot may be made of metals and some plastic links, and they are simulated via feedback control. So they will have a force feedback. So the moment you touch any object, just like when we hold a egg in our hand or a hammer in our hand, we know how much force to apply. Inherently, by nature, we know how much force to apply when we are hammering a nail and how much force to apply when we are cracking an egg. Similarly, we need to know how much force we need to apply when we are working with a rigid robot. So, a rigid robot will have a lot of high strength because it is very precise and it is metal links. So it can, as I was telling you in the previous slide, it will have enough strength to cause injury if it goes out of control. And that's where its weakness is. It's low behavioral diversity, and it's unsafe for humans. On the contrary, soft robots are inherently compliant. They can be made of fluids, gels, or even elastomers. Elastomeric materials like polymers, whose um, whose creation or origin ground is from the chemistry, where you're dealing with organic compounds like silicon rubber. Even there are some naturally growing elastomers, just like you have chitosan coming from seaweed. They can be used very easily as an elastomer. Some fluids like air, even water, even some gels. The best gel which I can tell you is, like baby diapers, which are used for uh, absorbing baby fluid. Um, that is also one of the biggest gel which is used. Even the gels are used in your contact lenses. So we are very much uh, surrounded by such material. Now, what if such material is used to make a robot? how powerful it will be, because it will have infinite degrees of freedom, it will have an adaptive grip, safe interactions, and it will have non-linear dynamics. When it comes to rigid links, it will have linear. Sometimes it is linear. Mostly it's linear dynamics. That means if I'm moving it by say 60 millimeters, it will move by 60 millimeters. But in the case of soft robot, it's not true, because it is more flexible. Even the fluid which is pressurizing it, it's more um, it's it is compressible, so it causes uh, control very difficult. So soft robots do not move differently, they just interact with the world differently. And the main purpose is they're relying on the material deformation rather than discrete joint rotations. That's a basic difference between soft robots and rigid robots. Many methods are used for actuating soft robots, like you can have some cable actuations. The best example is those smart material actuations, where you have a silicon rubber and you just pull a cable on the back end and it just causes bending of a material. If you push the tendon further, it can cause elongation. Similarly, you can have mimicking of the octopus um, method of increasing the size or decreasing its size. That happens because of the fluidic actuation. So when the moment you have fluid, it can basically cause the robot to inflate and deflate. You have pneumatic artificial muscles. This is also called as a McKeeban muscle. It is industrially available. You can also find it on regular commercial online shops, where you basically inflate it with air and it causes the bulging of the material. And it can basically, the moment it increases the diameter, it causes shrinkage of the length, which actually makes it feel like a normal human muscle. That's why it's called as pneumatic artificial muscle, or PAM. You have other materials like neonates, where you can basically create pockets of air, where you have channels which are supplying some fluid. And if you selectively control those fluid passing into separate pockets, you can actually cause uh, a normal motion, which is like more natural. You'll feel as if like somebody's crawling, like an earthworm. And if you make this series of components connected together, you can create a lot of robots like snake robots or earthworm robots and so on. C- Talking from the engineering perspective, as a normal rigid body will do, you'll just apply some stress and it will cause some strain. So it will keep on increasing its length to a certain point where it will just extend to a limit without beyond its elasticity and cause plastic deformation. That means the object will is almost on the verge of getting further deformed, and there will be a point where it will snap off. But in the case of soft material, it can basically go on elongating even further beyond the yield point, and it can come back to its original shape. That's the beauty of soft material. The formulas here are coming from the regular stress strain relationship. I won't go into details of it, but just to tell you in brief, stress is nothing but force upon area. So the force applied on simple materials can cause decrease or in the cross-sectional area, and hence cause elongation on the strain of the body. Let me take an example of the soft human hand. Uh, if I have to make it using a soft robot, how would I do that? Let's have a look at that. So a normal regular human hand can be replicated by providing some 3D printed base. Like here in this case, we can 3D print a normal base of a human hand using a ABS plastic, which can be 3D printed. Then you have some smart fingers, which can be pushed or pulled using some nitrile wires. As I was telling you previously in my slides about wires being pushed or pulled to cause a finger being bent. You can also have some tendons just like this, or you can have some nitinol materials. Nitinol is basically a biocompatible material. It is an alloy coming from mixture of two elements. One is nickel and titanium. Both of them are very much biocompatible. In fact, some of the materials are used for even braces when you wear on your teeth when people go for dentist appointments. Then silicon matrix, like a polymer, can be used to create a skin, an artificial skin. And then you have these tendon sheets, which can basically uh, route all those tendons to the actuator at the back end, which can push or pull or actuate this hand like a real hand. Now, let me talk about some smart materials here, like a shape memory alloy. There's a beautiful feature of these shape memory alloys, like nitinol, as I was telling you about nickel and titanium alloy. The main feature of this is that if you shape it to a particular position and then you heat it up, and then if you again let it remain in that position, and then when you leave it, if you leave it in that position and then you reheat it, it can basically remember its shape. So it's like you heat it to a certain position, you shape it in such a way, and then you heat it out back again, it will go back to its original position. So it's generally called shape memory. So it remembers its shape. So it's high stiffness when it's hot and flexible when it's cool. And this material is very much useful when you want to build any smart fingers like these from human inspiration. The field material, which is in the middle, which you see here, the blue colored material, that's called the eutectic alloy, which has a melting point of 62 degrees Celsius. It remains solid at room temperature and liquid when it is activated, and that causes the actuation of the finger, because it melts or softens the polymorphic plastic, and the variable stiffness based on the temperature gradient causes these kind of links to bend as if like a human finger. You can start with 3D printing such kind of material on a regular 3D printer, like using ABS, and then creating some molds, which allows for the tubings to go through the link lens, and then process the basic materials like heating it, heating the PCL processing, pre-processing material, so that the strands are rolled to a uniform rod like a tube, and then you use this material to cast into a mold. And once it is casted, you can pull them out using a nitinol pre-prep um, yeah, snippings, and those materials can be combined together to put it across. So this hollow end is the PCL, which is this pre-processing, and then the routing of this wire is the heating element, which causes the nitinol to heat to a certain temperature and then uh, cool it down to shape it back to its original shape. You can have different kind of rotation patterns or the wounding patterns, which can basically loop into different methods, and that may cause different methods of actuation. Once you have done that, then you can easily cast the silicon to mold the external sheath, and you can cause these tendons which you see here. These are just aligning all different elements together, and then you can have a liquid level. uh, Dragon skin is one such polymer material which is used to create the external skeleton, and when we pour them into the mold and we let it cure, you can actually create a real mimicked human hand at home. And this is how the tendon sheaths are pulled to cause movements and bending of the links. So as I was telling you about the nitinol memory effect, so it's when it's cooled, it is in flexible state. You actuate it, that means you pull it, and the finger curls. At that time, you heat it. So it is forcefully, and when it you apply the heat, it forcefully straightens at that position. When at that material, the material will melt, the action will be you are pulling the tendon back and the finger will curl back. So different materials which have opposing effects. Nitinol, which you apply the force or apply the heat, it will cause forceful straightening. And when you have the other material, the field metal, the PCl material, you cool it down, it will cause the curling back. As I was telling you about the soft materials, that it is very flexible. So modeling it becomes very difficult. This is a general equation which we generally use for creating any models of the soft material, where the first um term here just takes care about the inertia, and the second term takes care about the damping, any gravitational effect or stiffness of the material, which controls the torque or the force which we apply on these materials. So this is like a complete soft material which is divided into pieces. So this is called PCC, piecewise constant curvature, where you are dividing into individual pieces and you're controlling its motion. So for each element, you're concerned about the inertia, damping, gravitational effect, and stiffnesses to control the motion of the robot. So if I have to summarize, I would say that we have a control system to make a soft robot controlled. So for that, we need to know about the inverse kinematics. I'll tell you briefly about what does inverse kinematics mean. Suppose you have to hold an object in air. Suppose I have to hold this pen. It's kept in, say, this position, and this is my robot. I know I need to go to hold this position. I already know what is the XYZ position of this pen in the three-dimensional space. And I know this is my robotic arm. I need to go and hold it and pick it up and move it to another position. So, because I know the XYZ position of my end effector, I need to know about what will be the positions of my robotic arm. So, you're backtracking from your end effector's position and you're calculating what should be the motion of each joint of your robot. Because you're backtracking, that is called inverse. And what are you calculating? You're calculating the positions of each and every link of your robot. That's where the kinematics comes in. So because you knew the end effector's position and you are dealing with you're calculating the each and every link's position and robots control, the motors control, that's called inverse kinematics. The other way around, if you already know what position you are moving on the robot and you don't know where the end effector will go to, you just move your robot to a certain position and then you find out, oh, it has gone here. It was supposed to come here. That is called forward kinematics. So we need to know about the inverse kinematics, and that's very important in the case of soft robots because that allows it to control it and provide a feedback. That's where we bypass the complex physics equations, as I was telling you in the previous slide about these equations on the bottom. And then we are able to handle friction and we are able to handle trial and error, any sort of errors in control of soft robots. Now, given your given that I've provided you a brief overview of what soft robots is and what are the technical challenges, but there are certain areas where it has impacted a lot. Like soft robots have been used for rehabilitation of wearable and orthotics. Wearable devices are something which people are now using every day. Like in the case of patients who are suffering with, say, multiple sclerosis or patients who are dealing with Parkinson's disease, if we are able to make a patient wear a soft wearable upper hand brace, which can help them control its vibratory motions in the case of patients who are suffering from, say, Alzheimer's, that really helps the patient to recover and retrain itself. They can also provide haptic feedback. Haptic feedback literally means that when you're trying to touch an object, you get a force feedback on your skin. So, in the case of soft robots, these materials can be used to provide a haptic feedback. to the user. They exactly know how much force they need to apply on a given set of object. And it can be used for exploration of unstructured environment. In the case of, say, an environment which is suffering, which has been struck by, say, earthquake, where the entire structure is uneven, or for the sake of exploring another planet, like in the case people are very much excited about exploring Mars. So in such cases, soft robots can be very, very useful because they can mimic the human or nature's motion. So it's a convergence of soft, smart materials, flexible electronics, and learning about algorithms in creating new classes of machines that are safer, adaptable, and more alive. That's soft robotics for you. I'm going to talk about one application of soft robots where I have explored it for medical applications. This is about application in screening of or diagnosis of gastric cancer. Uh, Gastric cancer is huge problem around the world. It is almost like more than 1 million new stomach cancer cases are were reported in 2018, which was like 7% of the new cancer cases. At the moment, stomach cancer is very much prominent in the Pacific Rim belt, which comprises of countries like Korea, China, Japan, or even southern part of Asia, even certain west coast areas of uh, America region. Why? Because it's more about the food habits of people, also lifestyle driven. This work I had done some time back in University of Leeds when I was working there as a research fellow. The statistics and the state of gastric screening in has shown immense amount of gastric cancer cases coming up in the present scenario, particularly after COVID, when the world suffered from a lot of diseases which concatenated above respiratory diseases also. So how is it resolved at the moment? Generally, the doctor or the endoscopist wants to see around the stomach of a patient. What they do is the patient is lying on the left lateral position, and the patient is given a small pipe or a mouthpiece to bite on so that its teeth and tongue are out of the way when the endoscope is introduced into the patient. So the doctor basically introduces it through the mouth, and it goes through the esophagus into the stomach, into the first and the second turn of the intestine, which is generally called the duodenum and the duodenum. When the endoscope is introduced into the gastric upper gastric intestinal tract, it reaches to the end, and then the doctor basically pulls it back slowly. And whatever view is there on the screen, it sees it on its monitor. And what is it looking for? It's looking for any sort of lesions, as you can see on my screen. These kind of lesions can be any sort of polyps, or it can be um, any unnatural growth of tumorous tissue, which is in early stages. It's highly important to do this because if it is left unknown, then it can basically cause um, further stages of gastric cancer, which can be life threatening. So the device which is generally used for this kind of screening is a very bulky monitor which has a video processor and an audio monitors, which also it has uh, insufflation channel, which means that whatever body fluids are produced, there's a channel which sucks that out. And if there is any staining of the camera by touching on the skin, or any blood stain marks or tissue stain marks on the camera, there's a flush channel which basically flushes water and cleans the lens so that the view on the screen is clean. Such kind of device is a very high, bulky upfront cost. It's almost like $100,000 average. And every procedure would cost almost like $1,700 every procedure. And if in case you have used it on one patient and you want to use it for the next patient, you have to wait for it to reprocess it. That means you have to clean it, you have to autoclave it. That would almost cost almost like $150 to $200, and almost 76 to 90 minutes for reprocessing and cleaning it again so that it's used for the next patient. The usage of the device is quite bulky because the device is held in one hand and the doctor has to control the knobs, which looks like this, and it causes the motion. Though it's very useful, it's a very nice device, but it has some limitations. We tried to address this using the use of soft robots. As you can see on the screen, this is a work which we published some time ago. This is an endoscope, which is a low-cost disposable endoscope, which we built using soft robots. As you can see, the actuation, which is done using a continuum joystick, which pushes some air into some syringes, and this syringes causes the air to pressurize some bellows or some soft polymeric balloons, which causes this fluidic motion. A light source and a camera at the tip causes the light and the camera to produce an image on a video processor, which you can easily see on a tablet or a laptop. Such kind of device was used on different kind of patients. We tested it and we published the results. We further improved the design of the endoscope by joining all the three different balloons into a single monolithic system. Here you can see an entire endoscopic tip which was built using a single monolithic material. And this time we even reduced the diameter further. The previous version had a diameter of 13 millimeters. This time we produced it in a diameter of 9 millimeters. And we had a very typical method of building it because we had some helical cores, which were almost like screwing it. And then we prepared a mold in which we provided this silicon material. And once the mold was prepared, we took out the cores out by untwisting them to produce these cavities and actuated them with air to cause this kind of channel actuation and bending in 3 dimension. And we produced these results in some time ago in Frontiers of Robotics and AI. So if anybody who's interested, I would highly recommend you can go and read this paper. We further improved it because we wanted to integrate a camera in it. And then we also wanted to integrate other regular channels which were already available in the commercial device. So this idea came from origami. Some time back, I was playing around with some paper folding techniques, and I came across a very interesting patterns where the origami could be used to provide bending and elongating materials, and that quite intrigued me. So based on that, I started playing around with some paper folding methods, and I created like a hollow tube. And I found that okay, this is very interesting. Can we create some cavities just like the way I did that before? And I was able to create those cavities such that I could also have a central channel and um, three actuation channels, which we provided, and then we were able to control it. So this time, even along with the channel, we were able to reach to almost 8.5 millimeters in diameter. And here we provided the complete work space of this actuation of this material by using electromagnetic sensor on a EM field generator, which provided the position of and the bending space. This was again published some time back. Uh, so that's one application of soft robots in diagnosis. We are moving forward and we are trying to even integrate it into the camera and we are working on it. So that's a work in progress. So I'll talk about that sometime later if we have another chance to meet. Another application which I want to explore using soft robots is the area of rehabilitation. This is this is a case which is quite unique because in this case we are trying to prepare a device which can be implanted in the human body. If you remember what happened during the COVID time, people were on ventilators and they had an external ventilator like holding onto their nose and it was providing air and it was trying to inflate their lungs. Many people were able to survive, and it is a valid way of helping the patients to recover. But in some cases, if the patient has gone very chronic, or the patient is under um, is has gone into coma, in such cases, uh, the doctors have to wait until other medications are working. They cannot take the patient off the ventilator. And this is where the problem arises, because in a case like an epidemic, like an COVID, where patients are waiting for a place on a bed, it becomes very difficult to wean off a patient because we are waiting for another patient. And it's ethically uh, very incorrect that you just want to push off a patient because another patient is waiting for you, because life is very precious. So in our case, we tried to explore alternative ventilation techniques for ventilating the complex lung and diaphragm structures. And all this started with the context of a patient which I visited some time ago. Um, this was a time when I was invited. I was invited in a hospital, and I was on a hospital round with a clinician who took me to a patient who had a left lung diaphragm paralysis, and the patient had a very high uh, BMI. That means the body mass index was huge. And in the past, the patient was also a COVID patient, and it had a pacemaker. So the doctor talked to the patient, and he talked about that. Don't worry, we'll fix you today, and we'll, because your left lung diaphragm is paralyzed, we'll try to stitch it so that it doesn't trouble you. And the example which he gave him was very crude. He said that, have you seen a lady's purse? When you pull the string, or when you see a bag with kids take to the school, we just pull the string and it crumbles down. Just the way I will stitch your diaphragm. And literally he did the same. That's how the diaphragm was stitched. You see this? The diaphragm was stitched just like that, and it was bent, pushed down to the stomach or to the diaphragm. So overview is like when we inspire, when we breathe, even for public speakers or singers, when they deep inspiration, that causes your diaphragm to push down and your intercostal and the thoracic cavity to bulge out. And when you expire, the muscles contract and the diaphragm relaxes. So it comes back up. That's your exhalation. Now, in the case of patients who are chronic respiratory, they can't do that. They can't maintain the blood oxygen to a certain level, and neither they can expire the carbon dioxide out. In such cases, we we see this kind of case in different kind of respiratory conditions, like when you have conditions like acute respiratory distress syndrome, where the fluids start building up in the alveoli in the lungs. That can also come from pneumonia, even chronic obstructive pulmonary disorders, where the excessive uh, oxygen is basically not able to intake, and there is destruction of lung alveoli. This may also cause mucus production, and there is inflammation of bronchial tubes. That means the bronchial tubes become so inflamed that you are not able to breathe properly. That is where bronchitis comes in. In certain cases where patients are neuromuscular disorders, like the examples which I provided you before, like Alzheimer's or even Parkinson's, there the brain is unable to control the breathing. So in such cases, the respiratory muscles may become weakened inherently, and then they can cause failure. Or you have pulmonary edema. That means the lungs are affected um, by the inability of the heart to pump the blood. And that causes severe asthma as well. So in such cases, the traditional method is the invasive method. That means the patient is given a tube which goes through the mouth, and it enters into the trachea, and there's a ventilator which pressurizes air, and the gas exchange happens in the lungs. Now, what happens in this case is that because the tube has gone through the mouth, into the trachea, it has bypassed the regular or the natural the defense system of the respiratory system. So all your bacteria which is in the air or inside are directly getting in contact with the lungs, which may cause infection in long term, which is also called as ventilator associated pneumonia. So in one way, we're trying to help the patient, but it has a risk that patients can develop this pneumonia. So invasive ventilation is temporary until the patient is ready to wean off with other traditional methods. And invasive ventilation is associated with ventilator-induced infection, even barotrauma, tracheal injury, or even airway obstruction. And the primary reason for such high probability comes from the inherent nature of invasive ventilation, which bypasses the natural respiratory defense, which is coming from the hairs, tiny hair, or the cilia muscles in your nose, nostrils, or even in the respiratory tract. So our solution was that we wanted to develop a soft robotic actuator which could be implanted on the diaphragm of the patient, and we can cause basically a pressurization of the diaphragm which causes creation of negative pressure in the thoracic cavity, and that provides a natural hunger for the patient to breathe in. So, as a first level experiment, which we published also last year, uh, the the diaphragm is pressurized by these actuators, which we tested in different configurations. So we created like a dummy lung diaphragm in a laboratory. We're using again the silicon polymer, and we simulated the abdominal cavity with a regular box. Now you would imagine how can a regular box simulate an abdominal cavity? It was just more about simulating the pressure on the abdominal cavity. So the box was completely sealed in such a way that the diaphragm, whenever you pressurize, it creates a positive pressure in the abdominal cavity, which is almost opposite to the negative pressure created in the thoracic cavity. So this mimicked the physiological accuracy of the diaphragm and the rib topology, and an increase in abdominal pressure would yield a corresponding decline in intrathoracic pressure. So the test bed comprised of a silicon diaphragm, which was constructed of Diagon skin 10, which is a material which mimicked the human muscles property. And then we experimented. So we did basically pressurizing of the diaphragm and caused the contraction and expansion using these McKeban muscles. These are the same muscles which I was talking in my first slide, where I talked about those muscles which caused contraction when they got inflated with air. So we got to a certain position where we had different configurations, and we basically measured it. So I'll come directly to the results. So this is the kind of actuation which we did for for the different periods of motion, and we were able to achieve a peak actuation pressure of almost 250 to 240 kilopascals, which is a regular breathing pressure which we generally produce while we also breathe. In simple terms, this is almost like 5 centimeters of water pressure at room temperature. So the same process was repeated for different actuator configurations, and this results that we are able to show how abdominal pressure responds to peak actuator pressures. So the maximum pressure which increased for the change in abdominal pressure for each configuration was almost like 250 kilopascals, and the maximum decrease of the pressure was again 250 kilopascals. So this is just a result showing that how different configurations were able to achieve different pressures. So as an inference, this study was an important contribution which shows that on ex vivo models which we developed in the lab, we have seen we can generate repeatable results by removing subject variations, because every person is different, right? We as a human being are different from different people, and depending upon our breathing, age, gender, ethnicity, every person's um, breathing patterns are different. Also, in the case when we are running around, we are relaxed, that's also different. What will happen if the breathing pattern is for a chronic patient? That's again very different. So we are removing that subject variation by comparing different quantities and location of actuators, and we produce these results. But there are certain more areas which we are currently working on, like the geometry and location of these actuators over the diaphragm. We know that it's going to play a pivotal role in creating intrathoracic pressures. And with a straight medial configuration, we were able to increase the pressure about 5.5%. And in comparison to a branched geometry, we were targeting almost a posterior part of the diaphragm with a narrow configuration of almost 14.5%. And we exceeded the threshold of 5 centimeters water. We are trying to develop further with effective, safe methods of implantation because that's a practical challenge at the moment. So we are working on that, and we are doing rigorous testing on biocompatibility of these actuators because we don't want these actuators to cause any kind of sort of cytotoxicity in the humans. We will also be requiring to do some in vitro trials and also some patient trials. So that's almost on the developmental phase at the moment. Uh, so I'll stop here with a small vision, and I will say that the patients who do not wish to be supported by machines, that's the main area, but their poor health conditions do not allow to be weaned off. That's one of the areas where we are trying to locate and focus on using the soft robots. So I would thank you and open the floor for any sort of questions or comments. Happy to answer if there are any.
Excellent. That was really interesting, Manish. Thank you very much for that. We do have some questions already. So one of them came quite near the beginning of your talk when you were talking about the differences between hard robots and soft robots and the range of different robots you can get. And we've got a question from the audience, which is, can you have combination of soft robots and hard robots together? Is that something that you can make, or is there a reason you might want to do that?
Yeah, that's completely possible. Yes, soft robots and like rigid robots can be definitely combined together for various applications. Like just in the case where I was talking about the gastroscope, that's basically just the tip end is the soft robot. The rest of the tube is relatively rigid. That's one method of combining the soft and rigid robot together. Some cases where soft robots can be used for environmental um, explorations, or in the exploration in the case of um, exploring some unstructured environment. There also we can have some sampling units attached to the soft robots.
Excellent. So there's lots of compliments about the interesting talk that I'm going to echo, but I'll stick to the questions. So, um, there's a question. Somebody is clearly, as my uncle and my cousin are both big fans of 3D printing. This sounds like it's from a fan of 3D printing. This viewer wondered whether or not a 3D printed semi-rigid resin could allow for greater pliability and gripping than normal 3D printed bases. So for like the palm of the hand and things like that? Is there printing materials that would be good for uses rather than others?
So if I'm understanding, it says, I wonder whether 3D printed semi-rigid resin could allow for greater pliability for gripping. Uh, yes, it can, but there are certain limitations to the 3D printed. Like there are some elastic resins which can be used for 3D printing. I've used them, and sometimes they develop some cracks. It depends mostly on the kind of design which we are printing using the 3D printed resin. Uh, in short, yes, the answer is yes, we can do that. But we have to be very technically careful on how we can use it.
There's a couple of questions that I think might be related to each other. There's one about whether there's examples of soft robots combining with human flesh and muscle structures. And then there's another question that also asks about how do connected tissues respond to implanted robots? Is there a way that we can implant robots that would kind of interact with our own flesh in some way that is useful?
Yeah.
What's the latest advances in that field?
Yeah. So to first, I'll tell you about, like, if you have an implant, like a soft robotic implant in the human body, the body's first natural response is that it will directly develop a white, what is that called? It will basically cause inflammation initially. It basically goes and puts some protein layer on the top of the implanted device and tries to get rid of it, basically
Sort of
shut it away,
rejection stuff and things
rejections.
like that, isn't it? Yeah, yeah, absolutely.
So we need to do a lot of biocompatibility tests. So initially, when we develop any soft robot, we try to test by putting in touch with some some tissues coming from the say NHS bank tissue banks. We can get that, or even we can put in touch with some dummy tissues of, um, or we can create some in vitro environment of human body, like 37 degrees Celsius and 5% CO2. So we can let it remain in connection with those fluid matrix and see whether it has developed any inflammations or any bacterial growth. That helps you identify whether the material is cytotoxic or not. Once you have implanted, the question about muscle and soft robots getting along and interacting, that is definitely possible. And I am anticipating with my current project on soft robotic ventilation, it may happen. Because once the robot has been integrated onto the human body and the body accepts it, then the skin tissues try to grow on it as if it's the part of the body. So that is very much possible. It happens in the case of hip implants and knee implants. When in young patients, if you have any hip implant, like the the material is generally, again, uh, nitinol. Also, there are some other asbestos or ceramic materials which are used for implantation. In those materials, after some time, you will see that the patient actually has the growth of bone over the implant. So you don't need cement, bone cement. The implant itself has the bones growing over it. So in this case, also, I see that it is possible.
It's incredible, absolutely incredible. A couple more questions. There's a question, and I think this might already be true. What are the chances, what chances are that modeling or actual equipment will be funded by private companies or by the NHS? How do you interact with the medical industries, including companies and the health service?
So um, medical companies are very much interested in working with such kind of technology. Uh, like in my case, I have been connected with two of the industries who are working with me on this lung ventilation project. Some of them are actually providing me support for with developing some biomaterials for the product development of the implant, the soft robotic implant. And we have also connected with NHS. So some of the clinicians who are part of the NHS group, they are very excited to see this kind of technology developing, and they would like to do the initial trials on and help in validating its studies through a lot of trials. So it's not a very easy task. It's not a very easy road. It takes at least, I would say, 10 years minimum from a laboratory prototype to a fully functional device which is clinically validated, and then we go for any approvals to be used in patients. So
Yeah,
yeah,
that sounds great. There's a couple there's still more questions coming in. How do you see a place for biodegradable robots in the future? Would that be possible?
there are some robots which are already being developed. There are some published papers which are published in this domain. Uh, which the in immediately which I comes to my mind is, people generally use jelly, like a Haribo jelly. Uh, there are some. very futuristic um, drug delivery systems which are made from jellies now, which like patients can just pop in like a candy, and the material and the drug basically gets delivered, and the jellies disintegrates and comes out of the body naturally. So that's one area where biodegradable materials have been explored, but there are in the initial stages of testing. There's a lot to be done in that domain, but yes, people are very much excited and learning about it.
Yeah, there's a few, there's a little more interesting questions coming in. Um, This very close to my heart, if you'll excuse the pun, because two of my uncles have stents in their hearts, and the question is, could you create a stent which actively assists with heart function? That sounds like a clever idea, if it's possible.
So there's the current stents are generally made of nitinol material, and there's a very specific method called a TAVI process where uh, these these stents are basically introduced into the human arteries through the groin area, basically. So the surgeon basically pushes all this uh, through the veins, and it comes to the heart, and then it opens up the stent and leaves it there. These are passive stents; they remain in that position, and then over the period of time, if any further development of cholesterol or fat is there, then we have to keep on monitoring it. That's an exciting idea that a software bot which can actively assist a patient with assistant. Yes, it should be done, but I think I have not yet explored it yet.
Yeah, I
So
think that's
thank
it.
you.
There's such an exciting range of things that could be done. There's two questions, and I'll take these two, and then we might have to round up. One is about you mentioned Parkinson's, and then in a different part of the talk, I think you mentioned this idea that you have to do what did you call it? Reverse control, where you
Yeah, inverse kinematics.
inverse
Yeah.
kinematics. So the question I think might relate to that, but more a sort of software thing, which is how effective are soft robotics in providing haptic responses to Parkinson's patients who may not be interpreting the neurological responses correctly due to the Parkinson's. So in the sense that can the robotics interpolate or adjust to the neurological damage that the patient is already suffering? I guess that's what I think the question is aiming at.
Yeah. Uh, to answer, this is a fairly complicated question because every patient is quite different. Um, I would say, in short, yes, the answer is yes. But the route to interact with the patient who have suffering from Parkinson's and then learning about their haptic interactions, we would need to integrate with some sensors, uh, which is patient specific. So
Yeah, I
to
guess
answer
that's
it,
the
yes,
challenge.
it's a challenge.
Yeah.
It may not be very easy, but it is
And
possible.
and one more about route to market feels like the wrong route to patient, I guess. What about does robot apply in silico trials before the real life surgery? Is that how it works? Is that the process? So I guess is there simulation of the robots before they're used? I guess is
Yes,
the question.
so we generally trial, as I was saying, we test it in a in vitro environment, and then uh, we also test it in lab-based environment. So then we do like a phantom studies where we develop some dummy skin models and we test the performance of it. If in the case of biocompatibility, we test it in biocompatibility based experimentation.
And these are all
Finally,
experimental rather than computational or simulation. In
there
the
is simulation also involved with
yeah,
it.
yeah.
Parallelly, we do that. Then, if there is any need to be used in patients, before that, also there is a stage of animal trials. So that is also done very judiciously. We can't just do any sort of animal trials without thinking. So we have to be very careful. So
Of
then
course.
it comes to finally publishing it in the peer-reviewed journals, getting it validated with some. clinicians, and then going for patient trials.
Excellent. There's still questions coming in. Unfortunately, I think we're now out of time. Lots of interest about things like robots being used for rehab. I think the other thing to mention is that as well as this really interesting stuff, there's also work being done at York on things like how robots can be used for as nurses to help clothe people. There's robots
Yeah,
being used. There's robots that can design themselves in sort of genetic processes. There's a whole
yeah.
bunch of really exciting things going on at York. And unfortunately, the questions will continue to come in, I'm sure, but I'm gonna draw a line on this evening's, and just to let everybody know that the webinar has been recorded, it'll be available on the School of Physics, Engineering and Technology YouTube channel next week. A link will also be sent to all ticket holders. So if you're here, you'll get a link to that. So keep an eye out for your email if you want to have a look at that. If you want to attend any future events, whether it's the webinars or other things that we have going on at the school, the link is in the resources button on your screen. So have a click down there and have a look at some future events. Our next lecture will be on Monday, the 23rd of February, 2026, where Dr. Emily Brunsden will be speaking about using astroseismology to investigate how stars work. So going from the very practical medical all the way up to the stars. So lots of interesting things going on. Just left for me to thank Manish once again for
Thank
an
you.
incredible talk and all the viewers for the really interesting questions. And hopefully have a great night, a good week ahead, and hopefully we'll catch you at a future webinar. Thanks very much. Bye bye.
Thank you.